we'll start to talk about binomial coefficients and identities in this session. So this is the last leg of um, the entire chapter of counting. All right. Once we're done with binomial coefficients and identities, the discussions in under this topic will be done with counting. All right. So we'll start with this here, and we'll finish this up in the extra class on Saturday. And yeah, that also should tell you that the extra class on Saturdays, it's not just a tutorial. We will follow the syllabus very much. We will follow it like regular classes. So please make sure that you attend it, okay? Or at least listen to the recording later on. So yeah, so binomial coefficients will start here and we'll finish it up on Saturday, and then we'll start with induction. And the syllabus for quiz 5 is unit 5, entire unit 5. That is generalized permutation combination and then binomial coefficients and identities. We'll be done with this by Saturday for sure. Okay. So binomial coefficients. What is binomial coefficient? The reason we're talking about binomial coefficient is because NCR is sometimes called the binomial coefficient. Because in a binomial expansion, the coefficients in the generic theorem, the binomial theorem, the coefficients are represented using combination, NCR. Using this NCR combination, the coefficients are represented. That's why it's called the binomial coefficient. So this is the binomial theorem. This is the binomial theorem where you have this polynomial where if you expand it, this if the binomial expansion of this term here can be represented in this way, in a generic format in this way. That's the theorem. That if you have any term like this, x plus y to the power of some positive integer n, x plus y to the power of some positive, some non-negative integer n, some non-negative integer n, in that case, the expansion of this term would be done using this generic formula. That's the theorem, or this is the expansion basically. All right. And you'll see that in this expansion, every single one of the sum terms have the result of a combination as the coefficient. All right. The coefficient basically of every single sum term, the coefficient that will be multiplied with, that will be a part of the product term in every single sum term here in this expansion, is represented using NCJ. So we are using NCJ to represent the coefficients. So this is the binomial expansion, and the coefficients are being represented using NCJ. That's why NCJ is sometimes called the binomial coefficient, because it is the binomial coefficient. Numbers of the form NCJ are called binomial coefficients. All right. So first, let's look at this expansion. What's going on here? So they're saying that basically x plus y whole to the power of n, if you have something like that, the expansion can be done in this format. All right. That is, all the sum terms in the result will have the product of x, y, and a coefficient such that for j, for some j, some integer j starting from 0 to n, every single sum term can be represented using this format. NCJ multiplied with x to the power of n minus j multiplied with y to the power of j. See the first term where j is equal to 0. We'll start, the first value of j is 0, right? J starts from 0 and goes on until n. The first value of j is 0. For the first term, j is equal to 0. So what do we have here? NCJ. So NC0. So we have NC0 here. X to the power of n minus j. That is x to the power of n minus 0. So x to the power of n here, and y to the power of 0. Y to the power of 0 is what? Guys, y to the power of 0 would be equivalent to what?
1.
1. Exactly. X to the power of n multiplied with 1 gives us x to the power of n. The second term, how do we get that? The second term, we get that where j is equal to 1. 1 increment হবে, right? First term, j starts with 0 and then increments by 1. So j is equal to 1 now for the second term. If j is equal to 1, NCJ becomes NC1, and x to the power of n minus j becomes x to the power of n minus 1, y to the power of j becomes y to the power of 1. So this is the term you have. The third term, j is 2, so NC2, x to the power of n minus 2, y square. And so on until the second last term, where j is equal to n minus 1. All right, n minus 1. J is equal to n minus 1. So you have n, c, n minus 1. So here, NCn minus 1. And x to the power of n minus j becomes what? X to the power of n minus n plus 1. So basically x. And y to the power of j becomes y to the power of n minus 1. So you have this entire term here. And then finally, the last term where j is equal to n, the last value of j, j goes up to the limit of n. So the last value of j is n, so NCn, y to the power of n, all right? That is how the expansion works. This is the translation of this generic term into this, all right? This is just the generic summation. So if you expand it, this is how you do it. Now, this should be pretty straightforward to most of you guys, what I've discussed so far. But next, why is it that we can represent the coefficients in this expansion using combination? Why is it that every single coefficient is represented using NCJ? Why? How does it make sense? How does it work that NCJ, if you calculate NCJ, you will get the coefficient of every single term in the expansion. If you calculate NCJ, how does that work? Now to understand that, first let's look at a simpler case expansion. At a simpler expansion, x plus y whole cube. What is that? X cubed plus 3x squared plus 3xy squared plus y cubed. X plus y whole square. What is that?
A squared plus 2ab plus b squared.
X squared plus 2xy plus y squared. All right, x plus y whole square is that. Yeah, correct. So these are smaller expansions. So we know the formula for these things already, but these you get also from this binomial expansion. এখানে if you n is equal to 2 যদি ধরো, n equals to 2 যদি ধরো, এখানে যদি এটা apply করো, you will see that after applying this formula, n is equal to 2 এর জন্য, you will get exactly that, x squared plus 2xy plus y squared. If you take n to be 3, take n to be 3, then you apply 3 here. N is equal to 3 apply korle ekhane, you will see that you will get exactly x cubed plus 3x square y plus 3xy square plus y cube. All right, that's what you will get in the result after doing the expansion. That is what you will get. All right, so yeah, these are the expansions that you get from here as well. Now moving on to why is it that these coefficients, each of these coefficients can be represented using NCJ. Now, x plus y cube. Since this is a smaller expansion, let's first analyze that, what goes on here. The final term, the final expansion we have, the final result we have is x cubed plus 3x square y plus 3xy square plus y cube. The first term here is x cube. In order to get x cube, understand what we have to do. X plus y whole cube is x plus y multiplied with x plus y multiplied with x plus y. That is, in this entire product term, we have 3 sum terms. We have 3 sum terms in this entire product term. Yeah. And how will you get x cube? You get x cube if when you're multiplying. মানে এই যে এই পুরো জিনিসটা তো পাওয়া গেছে by multiplying each of these variables with each other, right? Now, how exactly is it that we got x cube? From the first term, we chose x to multiply with the second term. Now, in the second term as well, if you choose x, what do you get? X squared. And then in the third term as well, when you're multiplying, if you choose x, then you get what? X cube. So you get x cube only when you choose x all 3 times in this entire expression. All right? You have 3 terms here. You have 3 terms here. Each of these terms, if you choose x, that's when you get x cube. AGA x, AGA multiplication to kokhon pelam. See here. First, when we are multiplying x with this, we have xx plus xy, and then y with the rest, we have this. Fine. But then for multiplying with the rest of the term, x plus y, the rest of the x plus y term, if we choose this x here, this xx here, these 2 x's to multiply with this, only then we get this xxs, and that gives us x cube. So you have to choose x 3 times in all of these 3 terms. So for all of these 3 terms, every single time you have to choose x to get x cubed. Does it make sense?
Yes, ma'am.
Okay. How many ways are there to choose x every single time in these 3 sum terms? এই তিনটার মধ্যে every single time product টা determine করার জন্য, in order to get to the product, every single time choosing x, how many ways can you do that? How many ways are there to do that, to choose x every single time from these 3 sum terms, x plus y terms?
Three.
3 ways to choose x 3 times. Understand
I'm
what
confused.
we are doing. Understand what we are doing. Do you see x cubed টা পাওয়ার জন্য what do we have to do? So আমরা এখানে হচ্ছে কি product করছি, multiply করছি and all that blah blah blah, fine. But x cube termটা কিভাবে পেয়েছো? How did you get x cube? From the first term you chose x multiplied with this x from the second term. Hence you got xx, this one here. Then you again chose x from the third term here. Hence you got xxx, this one here. And that is the reason you got x cubed, right? Does that make sense? Do you understand that?
Yes, miss.
This is what I'm asking. How many ways are there to do this? See, we have 3 options here to choose from, right? 3 options, 3 terms.
There's one way.
There's only one way to do this. There's only one way to do this.
Yes, miss.
Exactly. There's only one way to do this. শুধুমাত্র একটা ওয়েতে এটা করা যায়. You see that no other case you will have where you have 3 x's. There is only one way to choose x all 3 times. You have 3 terms here, 3 sum terms here, 3 x plus y terms here, right? So you have 3 options basically. And from all of these 3 options, you choose x all 3 times, and only then you can get x cubed. So 3 options. From there, you choose x 3 times. So only then you get x cubed. How many ways are there to do that? 3 options, 3 times you're choosing. So there are 3C3 ways to do that. What is 3C3, guys? If you calculate 3C3, what is it?
1.
1, exactly. Also, remember that 3C3 is equivalent to 3C0. Also, if you look at it the other way, if you look at it from the perspective of y, the only way to get x cubed, this term, is if you never choose y from any of these terms. That is, you have 3 options to choose from, and you never choose y. You have 3 y's here, but you never choose any of them. How many ways are there to choose no y's from these 3 options? 3C0 ways. You're choosing y how many times? How many y are you choosing? Basically, koita y choose korcho? 0. How many options do you have? 3. So 3C0 ways to do that. 3C0 is equal to what? Again 1. All right. So you can look at it in any way. So that's what you get. All right. 3C0 or 3C3. If you think about it from the perspective of x, there are 3C3 ways to choose x 3 times. If you look at it from the perspective of y, there are 3C0 ways to not choose y at all, each of which give us 1. So there is only one way to do this. Since there is only one way to do this, that is the reason we have only one x cubed term. There is only one x cubed term. So there you go. Okay, next let's look at x square y. How many times do you have to choose x from these 3 terms in order to get x square?
Twice.
Twice. Very good. Exactly. Either you will choose x from the first term and then x again from the second term, but not from the third one. So you choose x twice. All right. Or you choose x from the first one, do not choose x from the second one, then choose y x again from the third one. So x is chosen from the first term and the third term. Again, x is chosen twice. That's another way. The other way is to not choose x, that is choose y from the first term, then choose x from the second and third terms. Again, you're choosing x twice. That's another way, all right? So first of all, you have to choose x 2 times in order to get x square. You have to choose x 2 times. Only if you choose x 2 times, you would have 2x's, which would give you x square. Xx would give you x square. And the other term, from the other term, if you choose x twice, then from the third term, which one would you have to choose? Obviously y. You'd have to choose y from the third term. If you choose x twice, then the other time you'd have to choose y, obviously. Duta term theke x choose korle, onno term ta theke, the third term, you have to choose y, obviously. So that's how you get x square y. Now, to answer the question, how many ways are there to choose 2x's from these 3 terms? We've already counted that. I've already counted that for you when I was doing the demonstration. How many ways are there to do this?
3.
3 ways to do this. Also, if you think about combinatorics, we have 3 options. We have 3 options to choose from. However, we choose x only twice. So 3 x's to choose from, but from them we choose only 2 of them, all right? So 3 options, and from there we choose x only twice. So 3C 2 ways, 3C 2 ways to choose x twice from these 3 options. 3C2 is equal to what? 3. 3C2 is also equivalent to 3C1. Also, if you think about y, if you choose x twice, then you have to choose y only once. You choose y exactly once. You have 3 options from there, you choose y only once. So how many ways are there to choose y only once from these 3 options? 3C1. Very good, exactly. So you have 3C2 ways to choose x, 2 x's, and 3C1 ways to choose y. It gives us the same thing, 3. There are basically 3 ways to get x square y. And since there are 3 ways, that is the reason we have 3 x square y's here, okay? 3টা way আছে বলে তো we have xxy, xyx, and yxx. 3টা different way আছে, and এই 3টা different way তে we get these 3 terms, xxy, xyx, yxx. And also notice that does order matter? The order in which you chose the x or the y, does that matter? কোন order এ choose করেছো? Whether you chose x from the first term and the second term, or whether you chose x from the second term and third term, does it matter? The order. Does it matter, the order? Does it matter?
No, miss.
No, it doesn't. So this is basically a task of choosing 2 x's from 3 options where order doesn't matter. So obviously, combination 3C2. Task of choosing 1 y from any one of these 3 terms. Order doesn't matter. So 3C1 ways to do that. So there you go. 3C1 ways to do that, which gives us 3. 3C2 or 3C2, which also gives us 3. And since there are 3 ways, we have 3 of these terms, which gives us 3x square y. We get 3x square y because there are 3 ways to do this, okay? For xy square as well. How many ways are there in terms of combination? In terms of combinatorics, how many ways are there to choose 1x from these 3 sum terms? How many ways are there to choose x only once from these 3 sum terms?
3C1.
3C1, exactly. And if you think about y, how many times would you have to choose y?
2 times, so it will be 3C2.
Exactly, which also gives us 3. Whichever way you take, it gives us 3. So basically, there are 3 ways to get to xy square. Since there are 3 ways to get to xy square, there will be 3 xy squares here. 3টা থাকবে এখানে। 3টা way আছে বলে তো 3টা xy square আছে। The summation of which gives us 3xy square. And y cube, the same argument as x cube, the same reason, you get 1 as the coefficient here for y cube, 3C0 or 3C3. Okay? Does everybody understand that? The explanation of how we get the coefficients here, each of the constants here, the coefficients here, how we get that from the concepts of combinatorics. Do you understand it for this one? Okay. Now let's talk about the generic case. In the generic case, what do we have here? X to the power of n minus j, y to the power of j. Okay. Now, first let's look at the first term here. The first term, when j is equal to 0, we get x to the power of n and nc 0. Now, how many sum terms do we have in this entire product term? X plus y whole to the power of n. কতগুলো x plus y থাকবে? How many x plus y's will be there? Here. Here, see x plus y whole cube. So we have 3x plus y. Yeah, that's correct. So we'll have n number of x plus y terms in the entire product term. That is n number of sum terms in this entire product term. Okay? So basically, we have n options to choose x. We have n options to choose x. And how many times do we have to choose x to get x to the power of n? X to the power of n power jona, how many times should we choose x?
N time.
N times, exactly. You have n x plus y terms. That is, you have n terms to choose from. That is, you have n terms where you can choose x. And in order to get x to the power of n exactly, you have to choose x all of those times. That is, n option আছে আর প্রত্যেকবারই আমার x choose করতে হবে. That is, all of the n times you have to choose x, right? So n options আছে. How many times do we have to choose x? N times. How many ways are there to do that? NC n ways. NC n ways to do that. Right? Yeah, one, obviously, one. But I mean, if you talk about the generic case without calculating if you talk about combinatorics and like expressing it in terms of combination, expressing it in terms of combination, it's NCN, right? N options to choose from, and you have to choose x n times. You have to make n choices of x from n option. Total number of option হচ্ছে কি n, because x plus y, there are total n number of x plus y terms. So total number of options to choose from is n, and from there you have to make n choices of x. That is, you have to choose x n times. So NCN. Also, NCN is equivalent to NC0. Also, if you think about it, in this term, x to the power of n, if you choose x n times, how many times will you choose y?
Miss 0.
0 times. We'll choose y 0 times, right? So if you look at it from the perspective of y, you have total n options to choose from. Just like before, here we had 3x plus y, so 3 options to choose from. Here we'll have n number of x plus y, so n options to choose from. So n options to choose from, but we choose y 0 times. So n option theke, if you make 0 choices from n options, it's NC0, right? So in other words, you can also represent it using NC0, which would give the same value basically. All right. What is the next term? X to the power of n minus 1 y. How many times do we have to choose x? How many times do we have to choose x to get x to the power of n minus 1?
n minus 1 times.
N minus 1 times. How many options are there to choose from in total?
N.
N. So total n options আছে. Total, you have n options to choose from, and from there, you choose x n minus 1 times. That is, you choose n minus 1 x's. How many ways are there to do that? How many ways are there to choose n minus 1 x's from n options in total?
Miss NCN minus 1.
Very good. NCN minus 1. NCN minus 1 is also equivalent to NC1. Also, if you look at it the other way around, if you look at it y, how many times can you choose y? Once you have chosen x n minus 1 times, x to the n minus 1 times choose karo. How many times can you choose y?
1.
The remaining option is only 1. All right? শুধুমাত্র একটা টার্মই তো অপশনের মধ্যে শুধুমাত্র একটা টার্ম বাকি থাকে. So you can choose y only once. All right? So if you choose y only once, you have n number of options. You're choosing y only once. You're choosing only one y. So NC1 ways to do that. There you go. And for the third term as well, as you can see here, y square. So you're choosing 2 y's from all of the n options. So NC2 ways to do that. And so on until the second last term where there are n minus 1 y's here. You have to choose y how many times for this one? N minus 1 times. How many options are there in total? N options. How many ways are there to choose n minus 1 y's from the total n number of options? NCN minus 1 ways. And the last term, where you have to choose y all of the times, just like the first case. Here, in the last case, you must choose y every single time. All right. So for all of the n options, you have to choose y. So you have n options in total, and you choose y n times. You choose n y's. So NC n ways to do that. Okay. Does it make sense so far? Any questions?
No, ma'am.
Okay. So if that makes sense, then the generic case should make sense as well. The generic case is just that, right? J is equal to 0 to n এর জন্য NCJ. J equals to 0 to n এর জন্যই তো NCJ. ওটা থেকে তো we get this, right? So in this generic term, what do we have? X to the power of n minus j, y to the power of j. In total, we have n options to choose from. In total, we have n number of x plus y terms. And from all of these terms, how many times do we have to choose x to get x to the power of n minus j? X to the power of n minus j. In order to get this, how many times would you have to choose x from all of the n terms?
Is n minus j.
N minus j times you have to choose x. Exactly. And if you choose x n minus j times, how many times can you choose y? You have chosen x n minus j times. Baki ar koita term thake? Ar koita x plus y term thake? If you have chosen x n minus j times, how many options are left? J number of options. Exactly. N minus j, x is already chosen. Left is j. So the rest of the j terms, the rest of the terms, you'll choose from the rest of the terms, you'll choose y. That is basically, if you choose x n minus j times, you can choose y how many times? J number of times. If you choose x n minus j times, then you have to choose y j times in total. Okay. You basically have to choose j number of y's from the n options. So if you choose j number of y's from a total number of n options, in that case, how many ways are there to do that? Total option ache koita? Total x plus y term. How many x plus y terms are there? N. So total options to choose from is n. How many y's are you choosing? J. How many ways are there to do that? NCJ ways to do that. All right?
Yes.
Okay. So there you go. That's all. That is the reason the coefficients can be represented using combination. Okay. That's how it makes sense. Because every single time you choose these product terms, every single time you choose these product terms, mean like the x and y, every single time you choose these x and y, you can think of it using combinatorics, using counting argument, and you can say that, okay, the number of times, based on the number of times you have to choose x, based on the number of times you have to choose y, you will get in total NCJ of these terms. All right, these terms will occur NCJ times. All right, that's what we can say. So that is the explanation here, written in short. Any questions regarding the explanation of or the proof of how the binomial coefficient can be represented using NCJ? This is just the proof which says that the binomial coefficient in this binomial expansion, the coefficient can be represented using NCJ. Any question?
No, ma'am.
No, miss.
Okay. So the reason binomial theorem is important is that because binomial theorem is used often for solving problems, and more importantly, the binomial theorem is used in many other theorems. Binomial theorem is the basis of binomial expansion, right? So it is used to prove many other identities, or to prove many other theorems, or make some other derivation. It's used pretty often for derivations, all right? That's why it's important in mathematics. That's the application, basically, of the most common applications of binomial theorem. However, we'll mostly focus on proving identities or solving problems using counting arguments and doing algebraic manipulations. So either using counting arguments or doing algebraic manipulation. However, you can you could also prove identities using the binomial theorem, but we'll mostly focus on how to prove identities on using counting arguments and algebraic derivation as well. All right, and that is what you should focus on for practice as well. However, it's also possible to do it using binomial theorem. We'll see examples of that as well, but later on. First, we'll look at examples where we prove an identity using counting arguments, yeah, and then using algebraic manipulation. Also, please notice that the binomial theorem, where the coefficient is represented by C and J, that proof is also done using counting arguments. আমরা যে proof করলাম যে NCJ, the fact that NCJ, it's correct to use NCJ to represent the coefficients of this expansion. This proof has also been done by counting arguments, by the way. All right, we've used combinatorics, right? We've used the definition of combination and definition. Combinatorics use করে, we've proved it. So that's also using counting arguments. Now, first, we'll prove this identity using counting arguments, and then we'll prove the same using algebraic manipulation. Now, Pascal's identity. It's quite famous. So we'll prove this one. And while we're proving this, I want you guys to focus on how counting arguments are being used here. All right. Proofটা তো পড়লে যে কোনো কেউ বুঝতে পারবে, বই লিখাই আছে, all right? You don't have to do it on your own. When it's done for you, it's very easy to understand. However, how is it exactly that we are using counting arguments to prove this? Please focus on that, because that is what you would have to do as well. You would be given with a completely new identity, which you would have to prove either using counting arguments or using algebraic manipulation or algebraic argument, all right? So if you have to use counting argument, you have to know how is it that we use counting argument to prove an identity. So focus on that here, okay? So here, to prove Pascal's identity, we will use the ideas of set theory and counting arguments. So before that, what is Pascal's identity? What does it say? It says that for two positive integers n and k, where n is greater than or equal to k, two such positive integers where n is greater than or equal to k, n plus 1 ck, this n plus 1 ck can be broken down into nck minus 1 and nck. Or the nck minus 1 and nck, the summation of these two gives us n plus 1 ck. That's Pascal's identity. You can use this identity to prove other things. In fact, even in the exam, for example, if you're asked to prove a certain identity, you're allowed to use Pascal's identity there. Why? Because we've already proved this. We've already done this in our sessions. You already know of Pascal's identity. If you see somewhere that, okay, Pascal's identity use kore, I can make my life easier, or derivation, it becomes easier. Algebraic manipulation bolo, or counting argument bolo, J method use koro. If you see that Pascal's identity helps you, you are allowed to use that, okay? You're allowed to use Pascal's identity there. For that matter, you are actually allowed to use all the identities and concepts that we've discussed so far, right? So you can use all of them, and Pascal's identity is one of them. So yeah, you can use that. Okay. Now moving on to the proof. How do we prove this? We will prove it using the ideas of set theory and counting arguments, right? Basically counting arguments in set theory, or set theory in counting arguments, whatever you call it. So n plus 1 ck is equal to nck minus 1 plus nck. That's what we have to prove. First, we will assume the existence of a set T which has n plus 1 elements in it. Okay, let's assume there is a set T which has in total n plus 1 elements in it. Okay, and let's assume that there is a particular element A in this set. A is one of the elements of this set. Let's assume that A is by default one of the elements of this set. So in that case, A is one of the n plus 1 elements, right? A is one of the n plus 1 elements.
Yes, miss.
Okay. Now we will try to form the subsets. We'll try to create the subsets of this set T which have the cardinality K. That is, we'll try to construct subsets which have total K elements, subsets of T which in total have k elements. The subsets have k elements. We'll try to create such subsets. How many ways are there to create such subsets? Think about it. In order to create a subset of T which has k elements, the subset contains in total k number of elements. In order to do that, what do you have to do? You basically have to choose elements from the parent set T te. How many elements do you have? How many elements are there in the parent set T? Guys? n plus 1. তার মানে কি এই n plus 1 elements থেকে আমার in total k number of elements choose করে সাবসেটে বসাতে হবে. That's how we will get a subset of T, right? Does it make sense? একটা এই সেটের সাবসেট বানানোর জন্য n plus 1 total elements আছে T তে in the set T. ওখান থেকে আমি k number of elements যদি choose করে একটা সেটে বসাই, we have a subset which has the cardinality k, right? So that's the way to do it. So the total number of subsets, if you think about it, the total number of subsets of T with cardinality k is actually the total number of ways to create the total number of ways to create these subsets of T. The total number of ways to create these subsets of T which have k elements in them. How many ways are there to create these subsets? How many ways are there to create these subsets of T which have k elements in them? The subsets have k elements. You have n plus 1 options to choose from. N plus 1 elements, n plus 1 distinct elements to choose from. You will choose how many elements in total? K elements. Exactly, k elements. How many ways are there to do that? N plus 1 ck. Why c? Why c? Because it's set and repetitions are not allowed, all right? And order doesn't matter, okay? So we are choosing k elements from a total of n plus 1 available options, and we are finding how many ways are there to do that. How many ways are there to choose k elements from a choice of n plus 1 distinct options? There are n plus 1 ck ways to do that. Why combination? Why are we using combination specifically and not permutation? Because in case of set, if you remember, order does not matter. The order in which you choose an element, will it matter in set? Let's say T set এ হচ্ছে গিয়ে elements আছে A, B, C, D. সাবসেটের মধ্যে তুমি চুজ করলা A, B, C. তুমি A আগে চুজ করো নাকি B আগে চুজ করো নাকি C আগে চুজ করো? Does it matter?
No, ma'am.
It does not matter. So order doesn't matter. We have n plus 1 options to choose from. We have to make k choices. We have to make k number of choices. So n plus 1 ck ways to do that. Okay? Does it make sense that the total number of subsets of T with size k is going to be n plus 1 ck? Does that make sense? Any questions so far? Guys, any questions?
No, miss.
Okay. So if you understand that, next what we will do is we will divide up these subsets into 2 categories, okay? The first group of subsets of size k contain the element A. The second group does not contain A, okay? We can divide it up in this way, right? One group of subsets, all of them contain A. The other group of subsets, none of them contain A. We can divide it up into these 2 groups, right? So again, remember that A is an element of T. A is one of these n plus 1 elements. Now we'll try to analyze each of these 2 groups individually. The first group of subsets with size k, all of which contain A. The first group of subsets which contain A, there, how many ways are there to construct the subsets of T with size k which contain A, which must contain A? How many ways are there to do that? How many subsets are there like that? See, originally, when we were just finding the total number of subsets, how many options do we have to choose from? N plus 1 options. Now you are saying that you have this group of subsets which contain the element A for sure. So you have already specified one of the elements, A. That is, you have already chosen one of the options. Total কতগুলো option ছিল originally? Originally, we had n plus 1 options. But the moment you say that all of these subsets must contain A, what are you doing? You're already choosing one of the options, right? Can we choose this option once again?
No, yes.
No, we cannot. আমাদের টোটাল ছিল n plus 1 options. ওখান থেকে আমরা already একটা option choose করে ফেলেছি, A. A is one of these n plus 1 elements, right? এখান থেকে আমি already A choose করে ফেলেছি. Since we have already chosen A, we cannot choose it again. So the number of options left to choose from is n. Does that make sense?
Yes, miss.
Okay. Now, that's the number of options left to choose from. How many choices do we have to make? Previously, we had to make k number of choices. We had to choose k elements previously. But now, when you have specified that A will be there for sure, in all of these subsets in this group, A will be there. Haven't you already chosen one of the elements? You've already chosen one of the elements, right? এই যে বলছো যে all of these subsets contain A. তার মানে কি একটা element already choose করা হয়ে গেছে. You've already made one of the choices. So if you've already chosen one of the elements, do you still have to make k choices?
No.
No. We've already made one of the choices. বলেছি যে A থাকবে, তার মানে একটা choice হয়ে গেছে. One decision has been made. One element of the subset has already been chosen. So the number of elements left to be chosen, or the number of choices left to be made, is k minus 1. Okay? So we have n options to choose from basically, and k minus 1 choices to make. So how many ways are there to do this? NCK minus 1 ways. That is, the total number of subsets of T with cardinality k that contain the element A would be NCK minus 1. Clear so far?
Miss, I have a question.
Yes, fine.
Miss, why are we dividing this into two categories? Like, to prove this theorem.
এই যে এই জিনিসটা প্রুফ করার জন্য. Okay, so yeah, good question there. Like, I think the better question would be, how do we know that if we divide it up in this way, we can prove this?
Yes,
Right?
miss. Yes, miss.
Okay. So you'll see that even when you go into proving, okay, I'll get to that after we're done with this proof. Yeah, Fahim, is that okay?
Yes, miss, sure.
Any other question regarding this, the fact that this, the total number of subsets in this group would be NCK minus 1? এটা নিয়ে কোনো question আছে?
মিস, জাস্ট একটা কোশ্চেন হলো এই যে এখানে যে কন্টেইনস এ, মানে এই এটা কোথায়? জাস্ট অলরেডি আমরা বলে দিচ্ছি এজন্য।
Contains A. এই যে we divided up the total number of subsets. We divided up into two categories. They contain A, they don't contain A. Subseটের মধ্যে তো A থাকতে পারে, নাও থাকতে পারে, right? এই যে n plus 1 CK, এই কাউন্টটা যেটা আছে, in this count you have subsets which might contain A, which might not contain A, right? সবগুলাই তো কাউন্ট করা হয়েছে.
Yes, miss.
If you think about it, can we not divide it up based on A, যে the subsets which contain A and the subsets which do not contain A, right?
Yeah.
Yeah, so we can divide it up in that way, right? So I mean, just based on that, we divided it up, and the total count of the subsets which contain A would be NCK minus 1. Okay. All right. Then let's handle the next group. The second group, where the total, we have to count the total number of subsets of T which have cardinality k but do not contain A. Okay. Now, in this group of subsets which do not contain A, notice what's happening. Originally, you had n plus 1 options to choose from. Okay. In the set T, you had n plus 1 elements, so n plus 1 options to choose from. However, if you say that these subsets cannot contain A, if you're saying that the subsets will not contain A, what are you doing? You're reducing one of the options. A was one of these n plus 1 elements, right? We had n plus 1 elements to choose from, including A. এখন যদি বলো যে A থাকতেই পারবে না, তার মানে কি A is not an option anymore. A is not an option at all. If A is not an option, do we still have n plus 1 elements to choose from?
No, miss.
No, we don't. We have n options to choose from, n elements to choose from. Because A is one of these elements. n plus 1 যে কাউন্টটা ছিল, that was including A. যদি বলি যে থাকতেই পারবে না, তাহলে তো একটা অপশন বাদই দিয়ে দিচ্ছি right at the start. All right? Right off the bat. So we don't have n plus 1 elements anymore because we are excluding A. Excluding A, we have n elements to choose from. So n options to choose from. Okay. Now, that's so far so good. Fine. However, have we chosen any element of the subsets yet? এই যে previous groupটা যেটা আগের গ্রুপটাতে দেখো, when we were saying contain A, because you say that they contain A, what does that mean? You're already choosing one element. One element has already been chosen. All right. However, in the second group, we're saying they do not contain A. All that does is exclude A from the option. However, have we chosen any element of the subset yet so far?
No, miss.
No, we haven't chosen any element. That is, there are still K choices left to be made. We still have to choose K elements from the available options. So we have n available options, and from there we have to choose K elements. How many ways are there to do that? NCK ways. That is, how many subsets? How many subsets would you have of T which have the cardinality K and do not contain A? It's NCK. Does that make sense? This part?
Yes, miss.
Okay. The required result follows. That is the reason we divided it up by A. Okay. So if you divide it up by A, all right, first of all, we can do that because the total number of subsets of cardinality K would be n plus 1 CK. We've already established that. Eta to establish korechi. A total number of subset er moddhe, you have subsets which contain A. You also have subsets which do not contain A. All right. So we don't know whether A will be there or not. However, we can divide up the subsets based on whether A is there or not. All right. We can divide it up into the total number of subsets which contain A and the total number of subsets which do not contain A. And if you sum these two up, you get what? The total number of subsets. Think about it. A group A, this group, the subsets which you will have, the subsets you will have in this group. Will you have any subset in common with this group? Will you have any subset here in the first group in common with the second group?
No, miss.
No. Simply because first এ সবগুলো subset A আছে, second টাতে নাই. So obviously কোনো common থাকবে না. So first we established that যে common কোনো কিছু নাই. So repetition of a count হবে না if you add these two. Also, if you add these two, you get the total number of subsets because একটা সাইডে আছে all of the subsets which contain A. First, তুমি যদি সবগুলো subset আলাদা করে নাও, think of the total, all the subsets. If you select all those subsets which contain A, all the subsets which contain A, if you bring them together and put them in a category, বাকি থাকে কোন subset গুলো? What are the subsets that are left? বাকি থাকে কোনগুলো? Only those which do not have A, as simple as that, right? You have n plus 1 CK total number of subsets. From there, if you bring out all those subsets, যেগুলোর মধ্যে A আছে, if you bring those out, count them and put them together, বাকি থাকে আর কি? বাকি থাকে only those subsets which do not contain A. All right. Either A will be there or A will not be there. অন্য কোনো possibility তো নাই, তাই না? So the rest of the subsets will not contain A. So obviously, the summation of these two will give us the total count of subsets, which is n plus 1 CK. All right. Or n plus 1 CK can be broken down into these two counts. Okay. So the reason we divided it up based on whether A is there or not, because this is one of the common approaches that we will take. You will see that when we do some of these identities, most often we will use the idea of a set and an element being in a set or not being in a set and a subset, okay? In counting argument, see, this is how we build things incrementally. First, mean, we did propositional logic because propositional logic is used in set theory, all right? Then we did set theory. Then the ideas of set theory, some of the ideas of set theories were proved using counting arguments as well. That is, we covered some concepts which combined counting arguments and set theory. Why did we do all of this? To get to here. Using the combination, using both counting argument and set theory, you can prove these things. And you will see that pretty often when you have to use counting arguments, যখন counting argument use করে কোন identity proof করবা, problem solve করবা, you'll see that one of the easiest way to do it is using set. Why is that? Because the idea of set is synonymous with combination. Counting argument মানে কি? Combinatorics, right? The idea of a set is synonymous with combinatorics. No repetitions allowed, choosing elements, also order doesn't matter. So it's very synonymous with combinatorics. So এসব identity proof করার সময় set theory অনেক বেশি use করা হয়. Set theory together with counting arguments. So often you will see that we'll use the idea of a set and some element or some elements being there or not being there and the idea of a subset. We'll use these things pretty often. এই যে আগে যে আমরা proof করেছি, for example, if you have n elements, then the total number of subsets would be 2 to the power of n or something like that. The reason we proved those things using counting arguments or using combinatorics, why did we do this? So that we can use those ideas here. ওই জিনিসগুলো কেন proof করা হয়েছিল? So that we can use those ideas here in proving identities using those ideas, okay? Say for example here, এই যে subset ideata je subset je mane creating a subset, you can do this using combination. Why does it make sense to you? Because we've already discussed this. Remember, in previous session we've already discussed these things. যে একটা সাবসেট বানানোর সময় আমি কম্বিনেশন অ্যাপ্লাই করে কম্বিনেশনের কনসেপ্ট গুলো অ্যাপ্লাই করে কেমনে একটা সাবসেট বানাতে পারি and how can we account all the subsets. Because of that, it makes sense to you, all right? So why did we do all of that? Because when you try to prove using counting arguments, a set theory idea use korle, it becomes a lot easy. And the idea of whether an element is there or not. See here, this is some combination, all right? These two are some combinations as well. What's on here? Eta, this one is being broken down into these two. This one is being broken down into these two. In order to represent this first one, we can use counting arguments and represent it in this way, that is subset. Subseter definition and counting argument use kore, we can represent it in this way. Now, Pascal's identity, what's going on? A n+1 ck, it's been broken down into these two. So also, আমরা subseter যে concept ওইটাও we will break it down. Since this is being broken down, আমরা subset will break it down based on whether an element is there or not. Why? Because if you break it down in this way, if you break it down on the idea of whether A is there or not, then later on, the result that you get, you can say that, okay, so summing them up, I can also get this, all right? Summing these up, we will get this. There will be no repetition. There will be no duplicate count. Also, the sum gives us this, all right? Do you get the idea of this now, Fahim? See here?
Yes, miss.
All right, so that's the proof. So first, basically, using subsets and the ideas of set theory and counting arguments, we showed that the total number of subsets would be n+1 ck. Then we broke it down into two categories, the ones that contain A and the ones that do not contain A. The ones that contain A, the total count for that is nck-1. That do not contain A would be nck. And if you sum these up, obviously you'll get the total count of subsets, all right? If you think about this group, this is the group of all those subsets which contain A. Baki thake ar ki? Ar baki thake only those subsets which do not contain A. So এই দুটোকে sum করলে তো এটা পাবোই. All right? And there will be no duplication of count since there obviously will never be anything in common among these two groups. All right? একটা দিয়ে
মিস এখানে যে আপনি বললেন যে কমন থাকবে না, বাট if there are 2 or more elements that are common, তখন কি করব?
বাকি কমন থাকলে কি হলো? সেটের ডেফিনিশন চিন্তা করো। সেটের ডেফিনিশন চিন্তা করো। একটা সেট চিন্তা করো 2 3 5, আরেকটা সেট চিন্তা করো 2 3 4. 2 3 is there in both of these sets, but এই দুটো সেট কি সেম?
না।
No. So are the sets in common? No. বাকি এলিমেন্ট কমন থাকুক কিনা it doesn't matter. Even if there is a difference of one element, একটা এলিমেন্ট ডিফারেন্ট হলেও তো the sets are different, right?
Yes, miss.
So there you go. Any other question?
No, miss.
Okay, so everybody understands this, the proof of Pascal's identity?
Yes, ma'am. Ma'am,
Good.
when will you upload the lecture 5 slides and recordings?
Oh, yeah, I haven't done that. Yeah, I'll do that today.
Okay,
Yeah,
ma'am.
class. Okay, thank you for reminding me that. Yeah. Okay, so proving the same identity using algebraic manipulation, right? This should be pretty straightforward to you guys. I'm sure you've done some of these things. I mean, algebraic manipulation, it's very common to us. We've been doing this since elementary school or whatever. So yeah, proving the same thing is using algebraic identity. Notice that we are moving from right-hand side to left-hand side here this time. In a comparison, we are moving from right-hand side to left-hand side this time, simply because it's easier. Think about it. N plus 1 ck. এটাতে তুমি combination formula apply করে, then breaking it down to this using algebra is a lot harder. However, algebrate combine করাটা আরো সহজ. If you remember algebraic manipulation, most of the time combining something and getting a more concise term is easier, right? So that's why we move from the right hand side to the left hand side. Right hand side হচ্ছে গিয়ে we have the sum of two terms. So এই দুটাকে algebra use করে, algebraic manipulation use করে, algebraic argument use করে, combining these two to get here would be easier. All right, that's how it works when we do algebraic derivation or manipulation or whatever. Okay, now, so the right hand side, nck plus nck minus 1. What is nck? If you apply the formula for combination, ncr ki chilo, remember, n factorial by n minus 1, r factorial into r factorial. So nck would be n factorial divided by n minus k factorial into k factorial. What is nck minus 1? N factorial divided by n minus k plus 1 factorial into k minus 1 factorial. So we get this just by applying the formula. Straightforward, nothing else. Okay. Now, next কি করেছে এটা বুঝার আগে চিন্তা করো next যেটা করেছে এটা কেন করেছে? Why was it done? That's the more important question. Why? Or what to do next? What should we focus on next? We have these two. What are we trying to do? We are trying to get to a more concise term, right? That is, we are trying to combine these terms. These two terms as it is, you cannot combine them. In order to combine them, what do you have to do? You have to have a common denominator. Denominator common থাকলেই তো তখন আমি combine করতে পারবো, right? So our next target should be making sure that these two sum terms have the same denominators. All right, making the denominator in common. Okay, that should be your next target in order to get to a more concise form. Now, how to do that? Look at what we have in the denominator. N minus k factorial here, n minus k plus 1 factorial and k minus 1 factorial here. Now, in these cases, it's smarter to look at the bigger factorial, because smaller factorial থেকে bigger factorial easily যাওয়া যায়. All right, it's easier to go to the bigger factorial from the smaller factorial. Let's compare the nk terms. Here we have n minus k factorial on this side, on the left hand side, n minus k plus 1 factorial on the right term. All right, first term we have n minus k factorial, and the second term has n minus k plus 1 factorial. দুটার মধ্যে which one is the bigger factorial?
N minus k plus 1.
N minus k plus 1 factorial is the bigger factorial, right? So it should tell you that n minus k factorial ke convert korata will be easier. Converting this one would be easier. Okay, how so? Think about it. If you have 5 factorial ke 6 factorial ke convert korte hole ki korte hobe? First you have to know what is 6 factorial. 6 factorial is equal to what, guys? 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Basically 6 multiplied with what? 6 এর সাথে the rest of them, what is that? 5 4 3 2 1. Exactly, 5 4 3 2 1. Etar product, the product of 5 4 3 2 1 is 5 factorial. So 6 factorial is actually equivalent to 6 multiplied with 5 factorial. Can we not say this? Yes, we can. So if we want to convert the smaller factorial to the larger factorial, what will we have to do? We'll have to multiply the next integer or the next term with the smaller factorial. 5 এর পরে next term কোনটা? 6. So if you multiply 6 with 5 factorial, as you can see here, you will get to the bigger factorial, 6 factorial, right? So now, let's see. We have n minus k factorial. We want to convert to what? N minus k plus 1 factorial. That's what we want to do, right? N minus k থেকে factorial থেকে n minus 1 k plus 1 factorial convert করতে যাচ্ছি, so that দোনোটা টার্মে we have the same factorial, okay? Basically, we have the same denominators আর কি. So n minus k factorial থেকে n minus k plus 1 এ convert করব. In order to do that, first, let's see what is n minus k plus 1 factorial. N minus k plus 1 factorial এটাকে expand করলে what do we get? We get n minus k plus 1 multiplied with n minus k, then n minus k minus 1, then n minus k minus 2, n minus k minus 3, and so on, right? So basically, if you bring out n minus k plus 1, n minus k plus 1, a term ta, if you bring that out, n minus k plus 1 বের করে আনলে বাকিটুকু, the rest of it, what is it?
n minus k factorial.
Exactly, n minus k factorial. So it's n minus k plus 1 multiplied with n minus k factorial. So আমি যদি n minus k factorial থেকে n minus k plus 1 factorial এ convert করতে চাই, what do I have to do? n minus k factorial এর সাথে কি করতে হবে?
n minus k plus 1 multiply করে দেব।
Exactly, that's what we did here, okay? See, n minus k plus 1 factorial এর সাথে we multiplied n minus k plus 1 for the purpose of making the denominators same, okay? And while we do that, we have to do the same thing to the numerator. This is pretty obvious. You should know this by now. When you do algebraic manipulation, there always has to be a way to go back, right? If you do something like this, then you have to make sure that you can go back. Denominator eta multiply korle obviously numerator eta multiply korte hobe. Otherwise, you won't be able to go back. That is this and this. They're not going to be equivalent. Okay, so n minus k plus 1 multiplied to denominator and numerator. So n minus k plus 1 multiplied with n minus k factorial would give us n minus k plus 1 factorial, which is the same as this term. Now let's look at the other product term, other term in the product. Let's look at the other term in the product. The other product terms are k factorial and k minus 1 factorial. Among these two, which one is the bigger factorial?
k factorial.
K factorial is the bigger one. So obviously, we will try to convert the smaller one to the bigger factorial because that is easier. What is k factorial equal to? K factorial is equal to k multiplied by k minus 1 multiplied by k minus 2, k minus 3, k minus 4, and so on. Basically, if you bring k out, k jodi ber kore ano, the rest of it can be represented using k minus 1 factorial, right? K factorial is equal to k into k minus 1 factorial. Does everyone agree with this? Just like this one here, 6 factorial is equal to 6 multiplied by 5 factorial. That is একটা comma, then next factorial. Decrement 1 and then next factorial. So k factorial is equal to k into k minus 12 factorial. Does everyone agree with this? Does this make sense? This is just factorial.
Yes,
Yes.
ma'am.
Yeah, okay. So if that makes sense, in that case, we have to convert from k minus 1 factorial. We have to convert from k minus 1. This k minus 1 factorial, this one has to be converted to k factorial. তাহলে আমাদের কি করতে হবে? What do we have to do to this product term to convert it to k factorial?
k into k minus 1 factorial.
Exactly, we have to do that. And while we do that, while we multiply k to the denominator to convert this to k factorial, we have to do the same to the numerator as well. We have to multiply k to the numerator as well for the same reasons, right? Okay, so yeah. So finally, what do you have here in the left term on the first term? N minus k plus 1 into n minus k factorial gives us what? N minus k plus 1 factorial, and then we have k factorial. So we have n minus k factorial. Sorry, we have n minus k plus 1 factorial into k factorial in the first term, the denominator of the first term. In the second term, the denominator of the second term, we already have n minus k plus 1 factorial, and this one gives us k factorial. So in the denominator as well, we'll get n minus k plus 1 factorial into k factorial. Now, the denominators are the same, right?
Yes, miss.
If the denominators are the same, we can take them in common. And then, what do we have? The common denominator here, and in the numerator, what will we do? We'll sum these up. A term ta. This numerator will be added with this numerator. এই দুটাকে যদি add করো, you have n factorial into n minus k plus 1, that plus n factorial into k. Donotate we have n factorial. We can take n factorial in common. If you take n factorial in common, what do you get? N minus k plus 1 plus k. So k gets cancelled out. Then what do you get? N factorial into what? N plus 1. What will be left? A term A. What will we be left with? N factorial into n plus 1. N factorial into n plus 1. What is that?
N plus 1
N
factorial.
plus 1 factorial.
Exactly. N plus 1 factorial. N plus 1 factorial, if you break it down, what do you get? N plus 1 multiplied with n factorial. That is what we have here. So you get n plus 1 factorial here. So n plus 1 factorial in the numerator, in the denominator, we have this. So far, does it make sense? Any questions so far?
No, miss.
Okay. So in that case, see, what is NCR? N factorial divided by n minus r factorial into r factorial. Here, n is n plus 1 and our r is k. N is n plus 1 and our r is k. Our n is n plus 1, our r is k. All right. So if you think about NCR, what is that? N factorial by n minus r factorial into r factorial. So here, n becomes n plus 1. So we have n plus 1 factorial in the numerator. And in the denominator, what will we have? N minus r factorial. So what does that mean? N plus 1 minus k. Exactly. Minus k factorial. This is that, right? This is exactly that. N plus 1 minus k factorial. This is the same, right? And then finally, r, in this case, which is going to be k factorial. So you have n plus 1 instead of n and k instead of r. So that's n plus 1 ck, right? So there you go. Algebraic manipulation, all right? So instead, if you understand the proof, very good. But the more important question here is why we took each of the steps, understanding that. The next step ta keno neya hoyeche, so that you can replicate that for your own proofs, all right? When you have to prove something using algebraic proof, just like counting argument. The next step ta keno kora hoyeche, ask yourself that first. Keno korche, acha korche eta ami buchhi, acha etar por eta hocche eta buchhi. But why is this being done? Eta keno kora hocche? Because first of all, why did we start from the right hand side? Because when it comes to algebraic manipulation, it's usually easier to combine multiple sum terms together and get to a more concise term. It's easier to do that. So that's why we started from the right hand side. Then we use the formula to just break the combination down into the factorials and all that, blah blah blah. Fine. Now, what is our goal? Our goal is to get to this term, which is more concise. That is, we'd have to combine these two terms somehow to get here. Otherwise, we won't be able to get here. The end that we want to get to, that is a more concise term, right? So we'd have to find a way to combine these two. And how would we combine these two? The only way to combine these two is only if they had the common denominator. The way it is right now, it's not possible. So denominator has to be common. So denominator ke common korte hobe, that is both the first term and the second term, both of these sum terms have to have the same denominator. Same denominator korar jonno C denominator ki ache. And then factorial gola dekhe, you have to understand that, okay, n minus k factorial ke ami n minus k plus 1 easily convert korte pari. How? By doing this. That's why we multiplied n minus k plus 1 to numerator and denominator. And same reason, k multiplied to the second term, denominator, numerator. And finally, we have the same thing. And it's pretty easy and straightforward. All right. So understand why every single step is being taken in counting argument and algebraic manipulation as well, algebraic argument as well. In both methods, algebraic argument use karo, counting argument use karo. In both methods, understand why every step is being taken. Yeah. Okay, any questions regarding Pascal's, the proof of Pascal's identity using both methods? Any questions?
No, miss.
All right, very good then. In that case, once again, I would like to remind you about the class, the extra class and the quiz. Please understand that the extra class will follow the syllabus, all right? It will be just like a regular class. So I would very much recommend attending that class. Even if you cannot, please give the recording a listen. When is the extra class, guys?
Miss, Saturday,
Saturday. At what time?
5 to 8.
5 to 7 p.m. actually.
Oh yeah.
5 to 7 p.m. 5 to 7 p.m. is the extra class. And when is quiz 4?
At 8.
No, miss.
7 p.m. It has been changed, remember?
I didn't see this. Sorry.
Yeah. All right. So see, updated schedule for the extra class is Saturday, 26 December. Sorry, I'm not sharing the tab. Updated schedule for the extra class is Saturday, 26 December, 5 p.m. to 7 p.m. And the updated schedule for the fourth quiz is the same day, 7 p.m. to 7:30 p.m. The syllabus is Unit 4, Basics of Counting. All right. So far, since there are no clashes, this is the schedule that we will follow. No clashes, this is what will happen. The finalized schedule for the extra class and the fourth quiz. And for quiz 5, there will be a slight change here, right? For quiz 5, instead of 5 p.m. to 5:30 p.m., we'll do 5:30 p.m. to 6 p.m. as per the request from one of the students. Yeah. So, yeah. Quiz 5, which will be on Monday, by the way, Monday, December 28. Monday, December 28, the quiz will be from 5:30 p.m. to 6 p.m. Okay. And the syllabus will be Unit 5. Okay. So yeah, everybody okay with that?
Yes, miss.
No clashes then.
Miss.
No,
All
miss.
right, good. Then that's finalized. That is the finalized schedule. So I'll see you guys on Saturday. Yeah, I'll end the recording here.